Hello, guys. Oh, too loud. I am Costa. I am the founder and CEO of Netdata. How many here use observability? I guess a lot. Huh? Open source or commercial solutions, what? Open source, how many open source? Grafana, Promethea? A few. Commercial? There are a few. Okay. Have you ever used machine learning in observability? Has anyone used machine learning? Not AI, machine chat, but machine learning? No one. Okay. So, guys, I will tell you what happened. Machine learning, artificial intelligence is a big thing. One subcategory is the conversational AI that we have today, but there is also machine learning, based on which also the AI, what we call AI, is based. Now, there was this interesting speech in 19. This is from Google. What Todd said back then was that observability, machine learning will never help observability. But if you read carefully, what it says is machine learning cannot solve most of the problems most people want it to. So this is an expectation. This is not that machine learning cannot do it, is that our expectations for machine learning are wrong. Now, in Netdata, since then, we were trying to make, and before what we call today AI, we try to experiment a lot with machine learning. How many do you know Netdata? Okay. And why you said no to open source software? Anyway, so we try to experiment a lot with machine learning from these times. And most of the users back then believed that, oh, this cannot be done, you know, this is stupid, you are wasting your time, et cetera, et cetera, et cetera. So, of course, the times has changed. And today, we have not only machine learning, Netdata is the only solution that has machine learning for all metrics. So no matter what you do, we train multiple machine learning models, and this is the presentation that we're going to see per metric in order to reduce false positives, etc. But also we have AI. And what is the toughest question you can ask an AI agent today? How many do you use? ChatGPT or Gemini or Claude with observability? No. With observability. Okay, no one almost. So if you ask this question, this is the toughest question you can ask. Hey, AI, how is my infrastructure today? Now look, most of them, what they will do by default. Get the alerts. Use a tool to get the alerts. Get the top nodes by CPU. If you have a bunch of nodes, they will get the CPU, the memory, the disk I/O, the last few error logs. And then, if you are lucky, they will try to do something deeper, but it's random. It's like totally random, because they don't have a clue. And then conclude. This is totally useless. It's totally random if they will find something. You understand why? Observability data are vast. So, especially if you're using the data, you are going to have thousands of metrics collected per server, applications, et cetera, vast amounts of logs. Where to look? That's the biggest problem. And all the work we have done in the data today pays off. Because today, the same AI agent, if you connect it to the data, it has these tools. The first is find anomalous metrics. So these are based, all three of them are based on a new engine that is inside every Netdata. It's a scoring engine. So most of the observability, all observability solutions have a query engine. You query the thing, and it returns you time series data. You have to select what you want, for how much time you want it, you get back time series data. This is a completely different story. This is a scoring engine, so it goes through all the metrics and tries to find the most offenders, or tries to find, this is, you select the algorithm, So the first one finds anomalies. The second one correlates metrics. The third one finds unstable metrics. And the beauty of this is that it can compare windows. So you can say, OK, I want for that time frame, but compare it to the previous one, etc. So with these tools, the AI agent now, the AI assistant now, by given only the time frame, right? How is my infrastructure today? That's only the time frame. It will use these three tools to actually tell you if you have a problem, where's the problem, and actually do root cause analysis. Now, in Netdata, these tools combined with everything else that we have is expressed with this AI chat stuff, LLM stuff, on dashboards. Ask AI is about any incident that you have, any alert. You can ask AI to actually troubleshoot and tell you why, what's this, and why it happens. A troubleshoot is you are on any dashboard. It doesn't matter where in the data. You have an AI troubleshoot button everywhere. This gets the context, what are you looking at, and tries to help you make sense of the data. AI Insights is about root cause analysis, capacity planning, performance monitoring, so whatever reporting you want, there is AI Insights. And AI Chat is that you connect it actually to your Gemini or Claude or GPT or whatever, and you chat with it with observability data. Now, what we have done in the data, why Netdata is different. That's the challenge that we had when we started. Netdata monitors 3,000 to 20,000 metrics per server, everything per second, by the way. So the data's design is distributed. Instead of centralizing all the data to some central databases, we distribute the code. So every Netdata agent is a complete monitoring pipeline. So when you install it in 1,000 servers, you have 1,000 independent observability pipelines. And then you can build centralization points, but as many as you want, not one. So you can aggregate data, build some centralization points here and there, depending on topology or service or whatever. And you can also, you can get infrastructure-level dashboards. We have a service, we call it Netdata Cloud. This distributes the queries. So when you want to query something that affects all 1,000 servers, in the worst-case scenario, and if there are no parents, no centralization points, we are going to do 1,000 queries. Each server will respond for itself. We will aggregate the data, show you the unified view that you want. Now, the challenge is that it's really a lot of data. This design, we did it like that in order to solve the scalability problem. All observability solutions tell you to select, to lower the resolution, the granularity, or control strictly the cardinality, how many stuff you collect. Why? Because at scale, these master databases that they have, they need treatment. They need huge babysitting. In the data, what we said is, OK, let's flip it. Instead of centralizing the data, we distribute the code. And then we have an engine on top of it that does distributed queries, like a distributed database. Observability data are vast. What was the goal? The goal is, first, to detect anomalies. So we want to know if the sample we just collected from any of these 3 to 20,000 metrics per server, it may be from CPU, disk, I/O, a database, whatever you have, it doesn't matter, message brokers, whatever. So we collected a sample, and the key question is this an outlier? Yes or no? Is this an outlier? How? Based on its past. Not based on something else that we trained somewhere else. Based on its past. Now, of course, we want this to be extremely lightweight because it runs at the edge. It learns metrics at the edge, patterns at the edge. And we want it to be totally unsupervised, so nothing for you to configure. It should just work. You install the data, boom, it works. There are things to tune, but it's not like the trivial machine, the usual machine learning that Datadog or Dynatrace sell. It's different. Now, I don't remember. How we do it? We train a new model, a new machine learning model every 3 hours, using 6 hours of data. So every 3 hours for every metric. Every 3 hours, we train a model that has 6 hours. So the models are overlapping. 3 hours is their time, but 6 in total, they overlap with the next, because in 3 hours, another one will be trained there. We create feature vectors. So this probably needs, let's take a car. You have a car. It has a speedometer. Do we learn on the speedometer? No. What we learn is on the delta of the speed. So we learn the patterns at which you accelerate or decelerate. And we don't train on one value. We train on 5. So we take 5 values, and we train the models on these sets, on the 5 values. This means that we know how you usually drive. Well, you're a gentle driver, well, you never brake, you never speed up like crazy. This is what we learn. The same thing, we learn it for every metric that you have, from databases to storage to sensors to temperatures to everything. So we learn how it behaves. And then we apply the k-means algorithm to find 2 clusters and get the min and max of these 2 clusters. What happens then is that the anomaly detection happens per model. So every 3 hours, a model per metric. When we collect a sample, we ask the model, take this sample, is this an outlier or not? Of course, there are some thresholds, but usually it's reliable. It has false positives. It's noisy. So what we do? The whole point here is to remember 1% anomaly, false rate, false positive, per metric, per model, per model. But what we do then is that we have 18 models. Why 18? We needed 18 in order to cover the last 2 days. The last 2 days, self-learning, many models, 18 models, and then when we add 1 and it becomes 19, we throw the first. So it forgets. That was the goal. If it learns an anomaly, it has to forget it at some point. So we have 18 models, but these 18 models, what they gave us is consensus. Now we have 18 models that need to agree that this sample is outlier. And this brings us to this. So the combined anomaly rate, the combined false positive rate, is this number. That's the 18 models, 1% of a model combined. Then when we had this, we started building more on top of it. So we said, if you put it on the servers and you start working on this and you see the anomalies that are happening, immediately you see that it's not one metric that gets anomalous. When you have an outage or a problem, it's a bunch of metrics. It's a lot. The disk is slow, the database became slow, so the patterns changed, and a lot of metrics together, all together become anomalous. When we realized that, we built host-level anomaly detection, host level. So Netdata is able to tell if the server is in risk. This is what this is. The false positive rate of this, it's a lot of zeros. It's 1,050 zeros. The false positive rate of this. Mainly because we need 30 anomalous metrics together. It's 1%. It's 30 at 3,000 metrics. So 1% of all metrics anomalous together. And each one of them, the tiny percentage that we had before. So this is a real outage. This is how it looks. The first chart is the percentage, so the y-axis that says 5 is 5%, is the percentage of metrics per node that went anomalous together. Every line, every color that you see is a node. And you see that on the outage, 5% of the metrics on a node went anomalous. The second chart is the absolute number of metrics that went anomalous per node. And you see that up to 2,000 metrics went anomalous concurrently. And the third is the host-level anomalies that Netdata detected. Now, this is I will go fast because we have only 3 minutes. This is a pipeline inside an agent. So you can see it collects data discovered, detects anomalies, time series database embedded into it, alerts, scoring, querying. Here you have AI assistants, MCP, streaming to create parent-child relationships, exporting to put it, if you want, to Influx or Prometheus or whatever, and the learning stuff. So this is each agent that you install. We did a lot of work to minimize CPU utilization of this machine learning. This is intensive in CPU. So we did a lot of work. Machine learning in Netdata doubles the CPU utilization of Netdata, but it was very small. So we went from 2%, 2.5% of a single core to 5% of a single core. So it's nothing. The memory is also ignorable. So we're talking about a few megabytes that you lose because of this. And on the storage, actually we changed the time series database is hours. So we changed the format and we embed it in a bit, the anomaly. So no extra storage on disk because of machine learning. What it can detect: spikes, missing periods, sudden dives, memory leaks and the likes. This is something like a memory leak. Sudden change of state. What it cannot detect short-lived workloads, so this needs time in order to be trained. It trains a model every 3 hours, and in order to reach the peak quality, it needs 18 models. So for something that starts and stops, doesn't help. Crashed services, so it needs metrics to detect anomalies. The absence of metrics that do not trigger anomalies on that thing, but they trigger around it. So that it will not be able to find anomalies on the server that crashed, but on everything else that depended on it. Let's go faster, 54 seconds. It's integrated everywhere. This is the data chart. Every Netdata chart is about 25 to 30 Grafana charts. So there are all kinds of stuff in order, data, observability data are like a cube. You can look at them like this, like this, like this. So this allows you, our charts allows you to pivot, regroup, slice, dice the data as you see fit, and even compare. Now we have an expanded view where it becomes double. The chart becomes double, and on the second section, we have comparisons to previous periods, how is it compared to yesterday, a week ago, etc. These are, again, UI features where anomaly is everywhere. Machine learning is first-class citizen in the data. The scoring engine we talked. 2 seconds, 1 minute. Do I have 1 minute? Because it's 0. We talked about this, highlights, unsupervised for all metrics, available everywhere, root cause analysis included. Netdata is a popular project. I think I don't have something else. That's it. And done.